Good morning, everyone. My name is Brian Phipps. I'm one of the engineers here at Monoxivent, and today's presentation is going to be focusing on source capture design. Kind of like 2 months ago, we had Mike Murphy give us an introduction to basic source capture design, and now Erik Swanson, the Monoxivent division manager, is going to kind of get a little bit more detailed on some of the source capture design. I'm sure many of you are familiar with Erik. For those of you that aren't, he's leading the source capture division. He's been with Monoxivent since the year 2000, provides frontline support for sales, representatives, end users. If you have any sort of questions or anything like that, he's definitely a guy that's always willing to help you out. A little bit of housekeeping before we get into the webinar. In the lower left corner of your screen, you see a little spot that allows you to type in questions. If you have any questions at any time throughout the presentation, we encourage you to type them into that box, send them off, and we'll do our best to answer them during the presentation. Now, without further ado, I'll go ahead and turn it over to Erik.
Thanks, Brian. Thanks, everybody, for attending this webinar. Like Brian said, we're going to try to expand a little bit on what Mike Murphy talked about in Design 101. First, I think we're going to go over some of the basics that he went over again. I mean, obviously, these are things you guys probably know. And, you know, these key terms and formulas don't apply only to our equipment. I'm sure you can apply these to all of the equipment that you guys sell in the HVAC industry. CFM is cubic feet per minute. It's a measure of air volume, of how much air we're actually moving in the system. Static pressure is basically the amount of friction that's being caused in the duct and in the system just by the sheer fact of the air moving through it. Feet per minute is a measure of speed. It's how fast the air is actually moving through the system, through the ductwork or through our hose. Or could even be considered as capture velocity at a tailpipe adapter or a welding nozzle, for example. RPM is rotational speed. This primarily deals with the fan. Obviously, the faster a fan spins, the more air it's going to move. The slower you spin it, it's going to move less air. It may take more RPM to move more air, or it may take more RPM to overcome more static pressure at a given CFM. So these are all important terms that you need to know. You got to know the difference between a CFM, an FPM, and an RPM to make all this make sense. One of the basic formulas, again, this applies to everything with moving air. Q over V times A. Q is the quantity, or the CFM. V is velocity in feet per minute, and area in square feet. So if we know any two of these, we can always figure out the third. For example, velocity times area in square feet is going to equal the CFM that we're moving. I mean, you guys that have done any air balancing at all, that's primarily what the air balancers do. They'll take a velocity rating in the duct times the free area of that duct, and that will tell them how much CFM is moving through the system at that particular point. Take quantity, divided it by velocity, and you've got the area, and quantity divided by area equals velocity. So this is a pretty helpful formula, and you probably use it all the time, and you just don't know it, but it's nice to see it on paper. Some of the things that are important to us when we are designing systems is what we're using for, or what we're up against as far as the engine size or the engine type. How the engines are running, what the size of the engine is, etc. This particular chart kind of breaks it down by engine type: 4-cycle diesel without a turbo, a 4-cycle diesel with a turbo, and a 4-cycle gas engine. We have some of the calculations already done for you. You can see the cubic inches typically on the left of the chart, and then the actual RPM that the engine might be running at, and the load that the engine's actually seeing. And you can see that it's important for us to know what not only the cubic inches of the engine, but also how it's being run, RPM and or load. Just for an example, if we look at an 800 cubic inch engine, turbo diesel, you can see at idling RPM 750, under no load, you're looking at about 220 CFM. An engine is nothing more than an air pump. If we know the volume, the size of the engine and how fast it's turning, we can, and what kind of load it's on, we can determine how much air is pumping out of that engine. Now you take that exact same engine, 800 cubic inches, and the extreme would be full RPM at 2100 under full load. You can see that exact same engine requires 3330 CFM of air. So just knowing the cubic inches, it typically isn't enough. And a lot of times we're asked to design a system around horsepower. You can see on this page that nothing on here talks about horsepower. It's all about cubic inches, RPM, and load. And obviously, as the cubic inches, RPM, and load change, the CFM required for our system is going to change as well. Now, if we don't know if the engine that you're working on does not fit one of these charts that we saw on the previous page, we have a calculation that we can take that cubic inch number, the RPM that they give us, and hopefully an exhaust gas temperature at the test RPM and load, and we can plug that into this formula, and it will basically tell us exactly how much that particular engine is pumping out at that condition. So again, cubic inches, RPM, which is the engine speed, and exhaust gas temperature, which is an indicator of load. The higher the temperature, the higher the load that it's under, the engine it's under. We can calculate out exactly how much air we need and how much we're going to need for our system when we're designing it. Some of the basic guidelines that we use, and these are for normal tune-up applications where the vehicles are primarily idling. They're doing routine maintenance, oil changes, air filter changes, brake jobs, you name it. They're not really revving the engines up too much. 300 CFM for cars and light trucks, 450 CFM for medium trucks and, say, school bus type applications, and 600 CFM for larger vehicles like dump trucks or over-the-road semis or even some of the industrial or ag equipment. Typical duct sizing is 2,000 to 2,500 feet per minute velocity. And I think you can see those basic formulas we were talking about before in terms CFM, FPM, RPM, they're all coming together here. They're important for us, and they should be important for you guys to get that kind of information when we're trying to size these systems. Some of the basics hoses that we use, 5000 series hose is a medium temperature for cars and light trucks, tune-up type applications. Get into diesel powered equipment that might be running higher exhaust gas temperatures, we like to use the 4000 series hose. And again, these are just the basic hoses for basic systems. We have other hoses available, and I think that we have a webinar also on our, I think on the website that goes into hoses in more detail, but for today's conversation, I think the 5000 and 4000 series hoses are going to cover what we need to know. And special consideration should be given to compressed natural gas buses or anything that runs compressed natural gas. It's not only buses that use it. I think buses is where it started. We are seeing more over-the-road semis and vehicles like that that are using compressed natural gas. Compressed natural gas burns hotter than diesel, so if there are vehicles that are burning that fuel, we need to know that so we can apply the appropriate hose. When we're doing a system, there's certain things that we have to complete it as far as our equipment goes. In this particular case, we're talking about a hose reel. It could be a simple hose or an underfloor system, but nevertheless, the basic items that the package would consist of are a hose reel, for example, the hose that we're going to apply to the hose reel, and then the tailpipe adapter that we're going to use to air at the right static pressure, some kind of a control system, on-off switch for the fan, or if it's a motorized hose reel, we may need an up-down switch for that. Diesel canes if we're doing trucks with vertical stacks, for example. Y kits if we're doing vehicles that have dual exhaust, 2 exhaust pipes on one vehicle. It could be trucks, cars, tractors, you name it. But if there's 2 exhaust pipes, we need to have 2 connections to that vehicle. So that's the basic package of information that we need and that we're going to apply to this particular job. Now, what we're going to do next is do a mock job, if you will. We're going to take the principles and things we talked about earlier here today, the CFM, FPM, apply it to a job, and actually do a design of a job so you can see the process, at least that I go through when I'm setting up an application. In this particular case, we're going to make it fairly simple. We're going to assume it's cars, trucks, light vans. I say Ford, Chevy, Chrysler, those are American cars. It could just as easily say Nissan, Honda, Acura, you name it. We're talking about passenger cars, light trucks in a tune-up application. There's not going to be a dyno in this particular facility where they're running engines under a load. We're not dealing with commercial or industrial equipment at all. There's no natural gas vehicles in this facility. It's all going to be gasoline or diesel-powered vehicles. And in this particular case, the engines are primarily going to be idling, and it's going to be a tune-up type application. This particular facility is going to have 8 work bays, and I did a quick sketch showing just the rough layout of what it's going to be. There's going to be basically an open building with 4 bays on each side. We're going to have a run of duct going to ultimately culminating in one duct that's going to go to the fan. And what we want to do now is take this basic design parameters that we have, the information that we've gleaned from the design worksheet. We want to put that on basically a piece of paper and design the system now, meaning size the ductwork and select some equipment to apply to this particular job. I'm doing this kind of old school with pencil and paper. And you can also see an old school ductilator to help size this, but I think you'll get the concept of what we're trying to do here. So my first step is I take the information that I've gathered with the design worksheet and I draw it out on a piece of paper. Here's where I'm envisioning the hose reels. Here's how the duct is going to be run and ultimately culminating in a fan. We know that in this case, it's going to be cars and light trucks. So we're talking about 300 CFM per vehicle or per hose reel in this case. And with that, we're going to use spring hose reels like they requested. I've selected a 5-9254 spring operated hose reel. That'll have 25 feet of 4-inch diameter 5000 series hose, a 23827 oval mouth tailpipe adapter, 23456 hose clamp. And again, this is going to be typical for 8 locations. Knowing that we have 300 CFM apiece, 8 locations, simple math, the fan's going to be 2400 CFM in the end.
Hey, Eric,
so
we've had a question come up. Let me interrupt you here quick.
Yep.
How do you design a system for a facility that has various types of vehicles in it? You know, maybe you've got them operating at different loads at different times. You know, maybe you've got like a larger, heavier pickup or bus operating in a place where you might also have a car.
Well, that's a good question, Brian. I guess we have 2 ways to approach that. One would be if in this particular facility they did not know exactly where the higher performance vehicles are going to be or the larger engine vehicles are going to be. Let's just take this picture as an example. If the larger vehicle could be in any of these 8 bays, we're going to have to size the hose reels for the larger vehicle. We have to be able to cover the largest vehicle in any bay. The other option would be to set aside certain bays that are going to be for the larger vehicles and make the rest of the bays for the smaller vehicles. That way we can size the bays for the larger vehicles with the appropriate CFM for that vehicle, and then the rest of them will remain the same. And now again, let's just look at this drawing, for example. If, let's say, 2 of the bays they were going to designate as the larger vehicle bays, and let's just say it's going to be the 2 bays closest to the fan, the one on the top and the one on the bottom. And let's just assume that those are going to be 600 CFM apiece, and then the remaining 6 are going to be 300 CFM apiece. So those 2 end hose reels that we've got arrowed there will be 600 CFM, and we'll use 6-inch diameter hose in that case, and the remainder of them will be 300 CFM inch diameter hose. And then ultimately the fan is going to have to be increased by 600 CFM, so it would be a 3000 CFM fan instead of 2400 in that case. Okay, so now if we're going to take and move it to the next step to where we're actually going to start sizing the ductwork, I like to start on the far left side or furthest away from the fan and work my way towards the fan. So in this case, we know that the first hose drops need 300 CFM. That first section of duct is going to run 300 CFM. So I go to my handy dandy ductilator, and you can see in this picture that it's pretty beat up. This thing's been around for a long time, and I can safely say I use it every day. But if we look on the right hand side for the air volume, CFM, we're looking for 300. Now we want the velocity, the feet per minute, to be between 2,000 and 2,500. Dialing this thing in, that shows us we need 5-inch diameter hose. Or I'm sorry, not hose, but ductwork. So 300 CFM is roughly 2,100 feet per minute, and that's going to give us a duct size of 5-inch diameter. So we're going to apply that to our drawing that we started earlier. And now I've circled in, these particular ducts are going to be 300 CFM, 2,100 feet per minute each, 5-inch diameter. So now to the next area of ductwork, now we've added another hose reel to each one. So our total volume through that particular duct is going to be 600. So we refer back to the ductilator again, looking at 600 CFM on the far right for our air volume. And we want to get in the 2,000 to 2,100 feet per minute range. That puts us comfortably into a 7-inch diameter duct. So with that said, these next sections of duct are going to be 600 CFM through that duct, 2,100 feet per minute through a 7-inch diameter. Now when we go just to the left of the second hose reels, you can see I've made like a little arrow point. That's where we're going to make the reduction from 7-inch to 5-inch. It's after that hose reel. So continuing on with this concept, the next section of duct is going to be 900 CFM. So going to the ductilator again, 900 CFM. We want to be between 2,000 and 2,500 feet per minute. That's going to put us into an 8-inch diameter duct. So now we want to take that, transfer it to our drawing. We got 900 CFM. That particular velocity is a little higher, 2,500 feet per minute, but we're within the range we want to be in. We're 8-inch diameter. Now we're adding another hose reel to it, so we're up to 1,200 CFM. 1,200 CFM on the ductilator between 2,000 and 2,500 feet per minute is a 10-inch diameter duct. So we're right in the range we want to be in. Transfer that to the drawing. Now we've got our duct runs on each side of the building are sized, and those ducts are ultimately going to come together in the middle to run to the fan. So now we've got our two 1,200 CFMs. We need to start looking at a 2,400 CFM duct. In this case, we're looking at 2,400 CFM again, 2,000 to 2,500 feet per minute, falls right in the middle of the range. 14-inch diameter is what we're going to select for that particular duct run. So now we have got our system totally laid out and designed. We know what hose reels we're going to use, what tailpipe adapters we're going to use, clamps, CFM is indicated for each drop. We've done the duct sizing all the way up into and including the fan. Another point that I'd like to make here is, and I'll talk about it in a minute, but you can see I show 45-degree lateral takeoffs at each takeoff to the hose reels. We want to use 45-degree laterals because they're a much better flowing fitting. Same thing with the Y fitting, where the two ducts or two 10-inch ducts are coming together to the 14. We want to use a Y in that case rather than a bolt type fitting. They're, again, much better flow. If we use a T, it will work, but you're going to have higher static pressure in the system. Higher static pressure is going to equal more horsepower requirements, could kick you into a bigger fan, but we want to keep the airflow as smooth as possible. Keep in mind, I guess an analogy for that is when you're trying to merge onto the interstate, they don't do it in a 90-degree angle. They have a nice smooth transition from you going down the ramp so you can get up to speed and blend into traffic without creating a bunch of havoc. That's the same thing with this airflow through this duct. If you've got duct air coming in at a 90-degree angle, especially when you get into higher velocities, it's going to create a lot of turbulence and a lot of static pressure. So now we want to talk about the duct construction. We've got the duct all sized. We know our system's going to be 2,400 CFM. In this particular case, we're going to be roughly 4 inches of static pressure, and we'll get into that in a minute. So with that said, we would recommend that you use the SMACNA negative 10-inch pressure class duct. It's a little bit heavier than the other -2 or -4 inch pressure classes, but you need that just to be able to handle the negative pressure in the system. Not only that, the higher static pressure construction is a heavier gauge, and in some cases we're going to have a little particulate running through the system. In the case of diesels, for example, you got diesel soot running through the system, which is highly abrasive. We don't want to wear the duct out just because of the dust, or in this case, diesel particulate running through it. So that heavier gauge material makes it a little more robust. We were talking a little bit earlier about the fittings. The laterals come in at a 45-degree rather than a straight T. Again, it's a much smoother transition for the airflow to make that turn. Same thing with the Ys. We're meeting at more of a 45 or a 90-degree angle included, which makes it a much smoother transition for the airflow and a lot less turbulence. Okay, now we had made the initial selections of the equipment. Now we're going to look at the actual data sheets for the equipment that we selected. In this case, it's spring-operated hose reels. I filled it in 4-inch diameter, 25 feet of 5000 series hose. This is going to be our model 5-9254 narrow body spring-operated hose reel. The hose that we're going to use for this application is our series 5000. It's a medium temperature, up to 550 degrees intermittent, 350 degrees continuous duty, and in a tune-up application, that's more than enough. You can see from the performance chart on the right, in this case 24 feet of hose, 4-inch diameter at 300 CFM is roughly 3 inches of static pressure. Keep in mind that that particular number is going to be a little bit of a moving target, because as the hose is wound and unwound onto the reel, the hose reel, that number can change. It can change quite a bit depending on having the hose completely wound up on it and taking a reading versus having the hose pulled perfectly straight off of it and taking a reading, are two entirely different numbers for static pressure. In this case, these numbers are based on roughly half the hose off the reel, so it's going to be close to where you're going to see where they're actually using the hose in the field on a vehicle. So with that, we got roughly 3 inches of pressure loss in the hose. And to that, we're going to have to add the pressure losses through the ductwork and any other accessories that might be in the airstream. A louver, for example, a discharge louver, add that to the total system static pressure, or dampers or other things to come up with our total system static pressure. Here's the tailpipe adapter, simple 23/827 oval mouth, rubber, chain and hook to hold it onto the vehicle, and the 23456 clamp that holds the pipe adapter to the end of the hose.
Eric, let me go ahead and stop you there. We'd had another 2 questions come in. Earlier you mentioned the intermittent versus continuous temperature use of the hose. Is there a limit to what intermittent defines? I mean, does that mean we can use it for 5 minutes at that temperature, 10 minutes, 20 minutes, or could you elaborate on that, please?
Well, with intermittent temperature, I think we're talking about just for short bursts of time, seconds, not minutes. We don't want to get, in that particular case, if you looked at the 5000 series hose, 550 degrees intermittent temperature, we can get it up to that temperature for a short period of time, and then we want to bring it right back down again. That particular hose, if you get over the 550, you will melt the fabric. You don't want to leave it that hot for an extended period of time because it will melt the hose. So when we're talking intermittent, we're talking seconds, not minutes or hours.
Thanks, Eric. And the other question, quick, is how does designing a system change what you've shown us so far based upon whether they're using hose reels, hose drops, maybe they're using different tailpipe adapters. Does any of that affect the design?
Those types of things are really not going to affect the design. What I think really affects the design is the CFM is what really affects what we've been talking about today. We've based our duct sizing on a certain CFM and a certain velocity. Changing the tailpipe adapter is not going to change the CFM. changing the hose type, if you will, from let's say a hose reel to a simple drop or a balancer drop. We still are going to have, say, 25 feet of hose to contend with, and that hose is still going to be 4-inch diameter, but the hose drop, because it is a balancer drop versus a hose reel, is really not going to change the way we're going to size the duct and the way we're going to treat the system. Okay, so next and finally, we have to select a fan for this particular application. You saw earlier on my the initial design sheet, because I knew the system was going to be 2400 CFM. So when we look at the actual performance chart for this fan, it's our BI 135, 13.5-inch wheel, backward inclined centrifugal vent set. When you look at 2400 on the CFM line versus 4 inches of static pressure, you can see those numbers come together right down the heart of the performance curve. It's right in the middle, right where you want to be. There's room to wiggle in this case. You could speed the fan up a little bit if we wanted to get 4.5 to 5 inches of static pressure out of it, or there may even be enough room there to add another hose drop to get another 300 CFM out of it if we were to speed the fan up a little bit, as long as we didn't alter the static pressure in the system tremendously. So that particular fan is going to be the choice in this particular case. 8 4-inch diameter hose reels, 2400 CFM. That would be the fan that we would suggest, particular system. So kind of wrapping things up here, looking at what we talked about today, cars and light trucks, 300 CFM, medium trucks, 450, larger trucks, 600. The velocity that we want to run, 2,000 to 2,500 feet per minute, is pretty consistent all the way through, no matter what type of vehicles we're working on. And in a system, simple system like this, as long as we're dealing with those parameters, the total static pressure in the system is going to be 4 to 4.5 inches. You saw in the chart that the hose itself was 3. That gives us 1 inch to 1.5 inches to play with for the duct system. There are ways that you can go through and calculate exactly what the duct system is going to be, but I think over the years we kind of figured out that inch and a half, as long as the duct system isn't tremendously long or doesn't have a bunch of crazy twists and turns in it, 1.5 inches is going to give you plenty to work with. 4,000 hose for the higher temperature applications, 5,000 for the standard cars and trucks. I think more importantly, up above, when we were talking about sizing of engines and how they're running, that's probably really, really important for us to know when we're trying to figure out how much CFM we really need for the system. We need to know cubic inches of the engine, RPM of the engine at any particular testing condition, and if they can tell us what the load is, and typically that's exhaust gas temperature, we can figure it out from there. But I think hopefully with what we've shown you today, you can do some of the basic systems that that we've drawn here. We see these systems every day. This isn't rocket science by any means, and a lot of the concepts and things that you're using here are not a whole lot different than if you were selecting a sealing diffuser or a louver or a fan for another application. We're all talking about air, CFM, and feet per minute, and velocity, and static pressure. So hopefully you found this educational, and you can use this in designing and selling our systems. Thank you all for coming.
Alrighty, thanks Eric, and thanks again to all our attendees. Certainly appreciate you taking time out of your busy schedules to join us this morning. Next month's webinar is going to be on the last Friday of the month. That'll be August 28th at 10 a.m. Central Time. We're going to be focusing on fiberglass reinforced plastic products at that presentation. If you had any questions we weren't able to get to, you had any sort of technical difficulties, or if you'd like a recording of the presentation or the PowerPoint itself, feel free to contact me, contact Eric, contact anyone at our support staff. I see Ed Smith just threw a question out there. Is your presentation available on the website? And the answer is yes. If you go to www.monoxivent.com, click on the Media Center tab, and click Webinars. They're all hosted on our YouTube channel, both the fiberglass and the source capture webinars. This one won't be up immediately. Usually it takes us about a week or two to get them edited and produced and put onto the YouTube channel, but we do keep record of them there. Thanks again, and have a great weekend.